Hello and welcome to the web series ZeroPM Pieces. In the ZeroPM Pieces, the researchers in the project will tell you about one piece of the ZeroPM puzzle that they're working on. So without further ado, here comes a ZeroPM piece.
I turn this week to talk about passive sampling, and then actually we're going to focus really on PM substances and the passive sampling of PM substances. So this presentation is going to be to present a status of passive sampling for polar substances, an insight into the principles behind passive sampling, and then a little bit on what kind of passive sampler configuration and calibration can we do for these substances. So why passive sampling? So passive sampling, very simply, it means taking a device that will deploy, most often deploy in the environment, where it will accumulate contaminants over time, and then we bring that device back into the laboratory and we extract it, analyze the amount of chemicals that have accumulated in that device, and then with some procedures which I will describe a little bit later on in this presentation, we calculate the concentration for that was in that environment for the period of exposure. So these devices are being developed for a wide range of contaminants. They are based on diffusive processes and will primarily estimate the dissolved concentration of chemicals, whether it's in water, it's in sediment, soil, pore water, and these tests can inform us on the accessible fraction of contaminants. The interesting aspect also is this integrative monitoring that can be done over periods of days and months, because for a lot of substances in the environment, the concentrations will vary over time, and if we have a tool with one measurement we can actually integrate the peaks and the changes in concentration, then we have a measurement that is actually quite attractive. In some cases, in many cases, but that's maybe more for the non-polar compounds, it really allows some improvements of limits of detection when compared with making a measurement in a water sample. And in some cases, we can use that also as to simplify the matrix of the sample we're going to be extracting and analyzing in the lab. So so we have this continuous monitoring. We can provide some time-weighted average concentrations for certain substances. We can relate what we see with a passive sampler to what bioaccumulates in organisms in water. On this aspect, we've done quite a bit of work on being able to compare the bioaccumulation in organisms with what we can predict, or not predict, but at least what we could consider would potentially bioaccumulate in organisms. And then in the end, also these samplers, when sampling different matrices like air, water, allow us to look at activity gradients and fluxes or differences in the level of contaminants in different environments. So in terms of the principles, passive sampling is really based on the absorption and diffusion of chemicals from, in that case, water. In this sort of conceptual model, the chemicals have to first diffuse across a diffusive boundary layer that forms at the surface of the sampler when deployed in water. The chemical then partitions to a membrane. It will transfer across this membrane and again distribute between the membrane and whatever sorbent or receiving phase that is placed at the back of the membrane. So that's a sort of most common way to design a passive sampling device. So going into slightly a few equations. So most of these equations are based on Fick's first law of diffusion. So if you have a concentration gradient, the flux across this surface area will be will be proportional to the difference in concentration gradient in between the two concentrations. So the way we look at, we have for our passive sampler a global mass transfer coefficient, and the sampling rate, which is expressed in liters per of water extracted by the sampler per unit of time per day. That is this mass transfer coefficient multiplied by the surface area of the sampler. So if you want to have a high sampling rate, then you need to increase, for example, the surface area. So that's a little bit how it works. Overall, the resistance to mass transfer of chemicals from water to a sampler is an additive model. So it's first the resistance across the boundary layer. So if you're in a very stagnant body of water, this layer will be very thick. If you have a sampling in a very fast flowing river, this boundary layer will be very thin, and then you realize from these equations that it will increase the sampling rate. And then we've got the resistance to mass transfer in the membrane and in the receiving phase, depending on the way the sampler is designed. So when we do calibration in the laboratory, most of these calibrations are aimed at measuring these partition coefficients or distribution coefficients, and then also measuring the diffusion or the transfer across whatever membrane is selected for the compounds that we're interested in. So in terms of the uptake, this is a general curve of contaminant accumulation over time into a passive sampler. So to start with, the concentration in the sampler or the mass accumulated increases proportionally to the concentration in water. And then if a device is left for a sufficiently long period of time, then you will reach this form of equilibrium at the end. For most of the polar substances, that most of this work with these substances, we're mostly interested being in this linear phase of uptake at the start, because this is where the mass accumulated will vary and will integrate mostly the changes in concentration. So we're for polar substances, we'd rather work with these within this area. In some cases, for example, when using absorption-based samplers like silicon LDP in sediments, we can set up some tests where we can actually bring, for most of the compounds we're interested in, we can actually bring the concentration in the sampler at equilibrium with the concentration in the sediment. So in these cases, we can actually work at the other end of this spectrum. So some of the challenges with passive sampling for polar substances, because a lot of the work done with the non-polar compounds has progressed really a lot over the last 20, 30 years, but for the polar substances, things have been a little bit slower. One recurrent issue is that for most of the types of passive sampler that exist, it's not possible to use these performance reference compounds. So these PRCs are usually spiked into samplers like silicon LDP, and these compounds that are not present in the environment will be released over time during exposure in the environment. And these compounds and the dissipation of these compounds will inform us on the kinetics of uptake into the samplers. So because of the way the samplers for polar chemicals work inherently differently, it's not really possible to use, and we in that case we can't actually know in situ what the sampling rates are. Then in some cases, especially for the very polar substances, things like glyphosates, and some of the compounds we are working with here, the challenge is even to find a receiving phase that has got a sufficient sorption capacity. Then we really need, because if we're doing deployments of these samplers in different water bodies, if the levels of turbulence of the water are different, we can have different sampling rates. So we need a way to be able to estimate these sampling rates in situ in our different situations. So there are different options that are available. that have been developed over the last 15 years. So you can, for example, deploy a non-polar sampler that will allow you to estimate what the mass transfer coefficient is for the water side of what happens. And then if you've calibrated your device, you can recalculate RS in situ from this. But it means having a second sampler. It does involve additional work. You can also use some alabaster plates. For example, there's quite a bit of work done with this, where the plate or gypsum plate will dissolve over time and will provide an estimate of this KW, this mass transfer coefficient in the boundary layer. Or the alternative is also to work with a sampler that is going to be insensitive to water turbulences. So you need to adjust the RS max so that the term at the end here in this equation becomes negligible for most of the KWs that we would see in the environment. So yeah, so in terms of sampler design, ideally, and that's where the research over the last maybe 10 years has focused, is to work with samplers where the mass transfer resistance in the membrane is much larger than what happens on the boundary layer side. So in terms of sampler configuration, the configuration will have an impact on the limits of detection, whether it's the surface area, or also in some cases the amount of receiving phase. It's going to also impact the time window for integrative sampling. And if we want to be able to have good limits of detection, and we might need to actually deploy samplers for quite a period of time. Then the choice, for example, of membrane will affect the sampling rate, also the selectivity of the sampler. The receiving phase will affect the sensitivity and the time to equilibrium as well. And then overall, the configuration and also you make the sampler, and you can choose materials that you can reliably source over time, will allow you to have a device that you can use accurately and precisely to derive CWs, freely dissolved concentrations, tomorrow and then in 2-3 years time or 10 years time. And then the calibration data will allow you to know how and the performance of your sampler. And then I think for these substances, we will be looking at different configuration of samplers for the different classes of chemicals. There will probably not be a universal sampler. So the different types and configuration of passive samplers that currently exist. So we've got this POCIS that was developed in the years 2000, 2005, I think, the first paper. So basically, it's a sorbent, SPE sorbent, sandwiched between two membranes. To start with, these membranes were made of polyether sulfone, and then different things have been tested over time. Here, the paper is referring to a study where our student Baptiste used a nylon membrane to be able to trap these wax, and it shall be sorbent to be able to sample PFAS. And then there's been a number of papers in the last few years as well on this NPT sampler, which is using a microporous polyethylene tube. It's a relatively thick tube, and basically the compounds are diffusing in these micropores in the water and accumulate into the sampler. So you see there's already some differences in surface area that is actually sampling chemicals. In the next device is this DGT. It was originally developed for sampling metals, but over the last 10 years also it's been, or even maybe more than now, it's maybe roughly 10 years, it's been applied to organic contaminants, and then some different types of gels and so on have been used for and adapted for different classes of chemicals. In that case, it's actually a paper from last year that where the DGT has been optimized for sampling melamine and other triazines. And you can see here that the sampling surface is again pretty much an order of magnitude below that of the POCIS. And then there's been a couple of papers with this G-tip sampler, which is this plastic container, and as you've got this little sampling window. So here the interesting thing is that you have quite a large volume of potentially receiving phase. In that case, your receiving phase can actually be even water. So you have 200 mL of water, for example, and then a small surface, sampling surface, which means that this sampler can actually, even though the receiving phase is water, it can actually sample integratively for a reasonable amount of time. So doing a tiny bit of very back of the envelope modeling, here we have our LOD analysis of a nanogram per sampler. We've got these range of reported sampling rates that are between 5 and 10 mLs, 2 to 5 for the G-tip, mLs per day sampled, from the surface area volume, and an exposure time of 15 days. We end up for most of these samplers with limits of detection that are in the low nanogram per liter. And then this DEQ is this degree of equilibrium. It's very artificial, but it's a calculation of with this sorption capacity of the receiving phase, how far are we from reaching this form of equilibrium or with the device. So are we still, if we are below 0.5, we should in principle still be sampling integratively. If we try to do a little bit of prospective modeling, so we go back to this equation here, and we use data from Vic Glanzman here, nice paper published this year, and they used we took the range of kWs from this paper and this equation to try to see what kind of RS max we should really try to target with our calibration and our selection of configuration. So here on the left-hand side, you have the current configuration of the devices we've been looking at. We're sampling about 10 mLs per day. We've got a surface area at 4 centimeters, and we see that our limit of detection will be in low nanogram per liter for an exposure of 30 days. And if we have high turbulences or low turbulences, so 3 micrometer per second or 18 micrometer per second for the mass transfer coefficient in the boundary layer, we see that our RS are very, very similar. So we won't have very much difference if we're sampling in a lake or if we are sampling in a torrent. If we want to try to decrease our limit of detection by at least an order of magnitude, to still sampling 30 days, we see that by increasing the surface area to 40 centimeters, and we've got a RS max of 0.3 liters per day, we see that for a very stagnant deployment, we could have a sampling rate of 0.23, and then for a much more rapid sort of high intensity water body, we will have a slightly higher sampling rate. In that case, the maximum that under these conditions would be RS max of 0.3. So we see would be between 0.23 and 0.3, which is, I think, a reasonably okay range of sampling rates. If we, for example, wanted to decrease this LOD to about 20 picogram per liter for this 30-day exposure, we could try to have something with RS max of 1.5 liter per day, so much higher sampling rate of the device itself. But then in these conditions, what we see is that if we are sampling a stagnant water body, we'd have a sampling rate of 0.6 liter per day. And then if we are sampling a very we would have a much higher sampling rate when in a very turbulent situation. So then we've got a much larger range of RS that would be obtained with such a device. And actually, some data to exemplify that. We had a deployment of some DGTs for PFAS over 21 days at 3 sites upstream and downstream of this paper factory in the Arnselva. And we see that with the DGT in gray here, it's below limits of detection, so we didn't detect anything. Our limits of detection, or actually quantification here, are in nanogram per liter, and they're actually very similar to the modeling we showed just before. If we used, when we used a POCIS sampler that was deployed for 63 days, we maximized the amount of sorbent that we put into that device, and we used this nylon membrane that allows much better exchange than other types of membranes. Then we see that we start to see things in the water. But again, we are in the low picogram per liter level. So here we have a sampler at the bottom where we know quite well the sampling rate, but it's not very sensitive. And then we've got above a sampler where we have much higher sampling rates, but the sampling rate will fluctuate a lot more with the water turbulences. But we do see things in the water. So we need to find a compromise between these two. In terms of passive sampler calibrations, there's different experiments that can be conducted with different levels of complexity. We can calibrate the different components of the sampler separately. So checking the sorption capacity of the receiving phase, we can evaluate the diffusion across a membrane. And then there's also the calibration with the whole device made. So you have calibrations like a single dose or static calibration. You have a beaker, you place your sampler into that beaker, and then you add your chemicals, you possibly agitate the experiment, and then you look at the decrease in concentration in the water. One challenge here is if you have, for example, a chemical that will sorb specifically to the membrane, then you might actually see a drop of concentration in the water, but that doesn't actually mean that the chemical has gone to the receiving phase. It might have just stopped on the membrane. So in these experiments, it's quite important to actually look at what's on the membrane and what's on the receiving phase. Then you've got some static renewal system. So it's the same system, but you change the water and spike again the chemicals you're interested in the water, so that the sampler is exposed to a concentration. It will vary a little bit, but to a concentration that is relatively constant over 5-10 days or whatever. And then the more the more time-consuming experiments are these flow-through or recirculating system, where you have a tank where you spike the chemicals into the tank with water flowing through this tank to be able to have constant concentration. And then you remove the devices over time, and then you build up your masses of chemicals accumulated in the devices over time. One important aspect here as well is that in these experiments, a lot of these experiments have been conducted for many polar chemicals, but there is a difficulty in knowing what the water boundary layer conditions were in these experiments, because you can't really translate RPM in the lab to a specific condition in situ. And then the last aspect to be able to do these calibrations is to do an in situ calibration. So you deploy a device at a specific site, and you take repeatedly some water samples to look at what the concentration over time in the water was. And then you have some samplers that are deployed for 1, 2, 5, 10, 20 days, however long you want to run this in situ calibration. So these are the different things that can be done. And now I'm going to go through a couple of slides where I'll show you how we've been doing some of these measurements. So we've been using this diffusion cell on the right-hand side here to look at the transfer across a stainless steel mesh with 5 micron openings to look at this naphthenic acid transfer. So you have a donor phase that is spiked with a chemical, and then a receiving phase, measure the compounds in the two sides of the setup. And then here we do a little bit of modeling to be able to find what our mass transfer coefficient is across our membrane. So in this system, we've run, for example, in that case, we've run multiple levels of turbulences, because again, in a test like this, you will have a mass transfer resistance in the membrane in the middle, but depending on how fast the system is agitated, you will also have some boundary layer developing at the surface of the membrane on each side. So all these need to be taken into account. One interesting and useful aspect with looking at these PM substances, here we've got a little bit of data for the uptake of TFA into DGT over 7 days, and we see that we have a nice accumulation. It's the fact that these compounds, if you're working with non-polar substances, it's quite difficult because these compounds tend to solve to anything, any surface that is in the system. When we're working with these very polar and that substances that like to stay in water, we don't have this problem. So here, a DGT exposure, the DGT can be placed into a bottle with 1-2 liters of water spiked with our compound of interest, because the sampling rate apparently here is actually quite low for this compound for the moment in these conditions. If the sampler is clearing 1 ml per day and you have 2 liters of water, then the sampler will not affect the concentration very much. So you can actually run some experiments very simply without having these flow through systems and so on. This is an example of a static renewal calibration for different PFAS compounds. So the water was renewed every day, experiments in 2-liter glasses. It was a POCIS sampler with a 10 micron nylon membrane, wax fluoroflash solvent mix. And here we see that we have a RS range that is actually very high, it's 0.7 to almost 6 liters per day. But that's because of this nylon membrane that is with quite large pores. And then finally, one possibility also, and that's a system that we had running last week in the lab. It's a sort of full-scale calibration where you have devices that are exposed to water. In that case, we have water that is recirculating. What you can do is expose multiple samplers simultaneously, and remove the samplers over time, and you can take water samples also over time to track what the concentration is, and then you can evaluate these sampling rates under constant water, or as constant as possible, water concentrations. And then here we've got a constant and repeatable steering as well, which is quite important. And in that case, that experiment was actually run also with silicon rubber spiked with PRCs, and then these PRCs were actually dissipating into the water and were telling us what this mass transfer coefficient KW was for this system with this rotation speed. And in conclusion, I think we have a number of promising passive sampler configuration that are possible, that can be further improved to sample PM substances. And as shown in these slides, we also have tools, techniques, and some experimental procedures that we are getting that we get to know quite well to be able to do these robust passive sampler calibrations. So, and with this last slide, I'd like to thank Sarah, Baptiste, Håkon, Pepo, Sarah, and Max that one way or another have contributed to the work that was on these slides, and of course ZeroPM for funding our work. Thank you.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.